So right, so we'll continue from the point that we stopped last week. So we started a discussion on NoSQL databases. So I began a brief introduction to NoSQL database model, and I did a comparison between the relational data model and the NoSQL databases, and pointed out why the NoSQL databases are required. That means the motivation for NoSQL databases. So I emphasize that it depends on the use case because of some of the shortcomings of the traditional relational databases, such as impedance mismatch. That is the mismatch between the representational data model in the relational databases and the hierarchical data structures of the memory. Hierarchical data structures of the memory, right? Then I told you that there are 4 types of basic NoSQL databases, and also out of that, we can categorize them based on 2 types. So those were the aggregation model and the graph or hierarchy graph database model. Aggregation or the hierarchical model, and the graph, or in other terms, the network model. And about the aggregation model, I pointed out some facts. So we now we'll focus on this distribution model, which is common to both the aggregation model and the graph model. That means I'm talking about overall NoSQL database. So what is this distribution? So we'll have a look at what is meant by that. So in relational databases, there is no requirement of distributing the data, because in the hierarchy or the architecture of the relational databases is that there is a centralized server. That means the data resides in a central server where different users can log in and perform their transactions, right? But in NoSQL, I explained last week that it is based on clustered servers. That means there is a group of servers known as a cluster. So this data distribution can be done in a cluster of servers. So there are 2 main methods of distribution, known as replication and sharding. So now we are going to discuss what each means, right? So we'll first take a look at what this sharding is. Sharding means distributing data, but not copying across multiple servers. So what this means is, so to give you a good understanding, I'll take an example of a relational model. So this relational model is not applicable to this NoSQL databases, but to give you understanding, I'll take an example from relational databases. Consider a table in a relational model. So in a relational model, in a table, there are many rows. And in relational model, all of these rows are stored in a particular server. But in NoSQL databases, as there are multiple servers which can store data, different parts of that table, different parts in the sense different rows or groups of rows, different groups of the same table is stored in different servers. That means part of the same table is stored at different places, which is not like the cases of relational model. In relational model, a single table is stored at a particular point or particular server. But in this sharding mode of distribution, what it does is for a given subset of data, for subset of data in the sense it can be a key value store, a single key value store, or it can be a column family store, or a document type database. But the fact is, it is that subset of data is spread across different servers, I mean different places. If you want to get the whole subset, you have to access different these nodes, different these servers, right? That is a kind of distributing a subset of data within different servers. So that is what it is meant by sharding, right? So by using sharding, you can spread a subset of data in different servers. But in contrast to that, what does the replication means? Replication is copying. Replication, the simple definition is copy. Data is copy. That means same subset of data appears across multiple servers. Appears across multiple servers. That is done in order to secure the durability of data. That means suppose that some of your data is stored in some server. If in case that server is down, so there should be another secondary or tertiary way of having access to that data. So the data may not be accessible due to network failures or hardware failures or due to authentication problems. Maybe you don't forget, you have forgotten the password, then you will not be able to access that particular. So likewise, there can be different cases by the day you will not be able to access a different data in a server. So what does this replication does is, so it to increase the availability of data. This replication is done, and also to protect the durability of data, this is done. Replication, that means copying the same data in different servers, as you have multiple servers in NoSQL databases, right? So these are the two modes, and in this replication, there is two ways of replicating. The same process replication is done, but there are two modes. So for a given NoSQL database, whether to use sharding or whether to use replication depends on what type of use case is required. So if we have a theorem known as CAT theorem that we will discuss in today, which states that out of consistency, availability, and partition tolerance, only two can be achieved at a time. So based on what you need to achieve, whether if you want to achieve consistency and availability, then you will have to choose one of these. If you want to increase the availability, you can use replication. You can use replication, right? If you want to increase the consistency of data, so consistency means agreement between data. if you want to increase the consistency of data, then it is better to use sharding. So based on what you need to achieve for your database system, I mean specifically for NoSQL database system, right? So whether to use sharding or replication is dependent. So some system may use a combination of this, where the degree of replication may be higher or lesser than the sharding, right? So that depends on your requirement, right? So as I told you, this replication can be done in two ways, that is master-slave mode and peer-to-peer replication, right? In master-slave replication, so these nodes are nothing but servers. Server means uh, a unit which can act as a storage for the database system, which can respond to user transactions, whether it is a read operation or whether it is a write operation. The server should be able to respond. And as there are many servers, there are two ways of doing this replication. That the first mode is this one, master slave replication. That means for a given set of servers, there is a master. Master is the one who controls, master is the server which controls the other servers. Other servers means those servers are known as slaves. So there is master-slave relationship, which the slave should get the consent of the master in order to do his operation. So in this particular case for master-slave replication, so the conflicts usually arise in writes. So in reading there is no conflict, because as long as the data is not updated, reading from any copied node by a user is okay. So then there is no need to get permission for the slave servers or slave nodes. There is no requirement to obtain the permission from the master node by the slave nodes, because reading, there are no conflicts in reading. I mean, the reading is consistent as long as there are no writes. So writing is the process which can cause conflicts, because in replication there are same copies of the same data. I mean, copies of the same data are there. For example, assume there are 3 servers. The same data is copied in 3 servers. So if a user comes and update the data in one server, that same data should be updated in the other 2 servers also. That same data should be updated in the other 2 servers also. So otherwise, what happens is the data is inconsistent. That means the data which is read from the server 3 does not agree with the data the same data read from the server 1, which an update operation was happened a moment ago. So as I pointed out, so the writes are the operations which should be handled. So in this master-slave replication mode, the master will handle the write operation, and it will synchronize with the slaves and handle these write operations. And in just after a write operation, So masters should be responsible that the read operations are consistent. So in some way, this master and slaves should synchronize with each other to make sure that the reads after after a write operation is not inconsistent. So this is how this master slave replication mode operates. So the master handles the writes, and the slaves and master synchronize with each other to handle reads, because the reads are not much prioritized as writes. Okay. The second mode, as I told you, is peer-to-peer replication, where that authority of the master is given to all the nodes. That means there is no master, there is no slave. All are peers. That means all are having equal privileges of reading and writing. There is no governing body. That means in this case, the reading and writing is done by peer-to-peer coordination. Peer-to-peer coordination. If there is a write operation, then that node will allow writing. Then that node will synchronize with the other peer nodes and say to the other nodes that this particular data has been updated. So there is a way of telling that, right? So that is called as version stamps and version vectors. That part also we will discuss today. That means when in this kind of replication, that when one node is updated, other nodes must also be updated. Other nodes also must be updated. So in master slave mode, master will control this one. In peer-to-peer replication mode, all the nodes will synchronize and control this copying of data. Right. So these are the two ways. So there are pros and cons of each of these two modes, right? So there is this advantage of reducing the chance of update conflicts in a master slave mode. So that means, for example, suppose that two users want to update the same data. If two users want to update the same data, they have to obtain the permission from the same master. Then master will allow one user to update first, then he will allow he means this server will allow the other user to update next, or may reject the request from the second user and allow only the first user. Master will decide. So there will not be any conflict. But in peer-to-peer replication, there can be conflicts when two users update the same data at the same instant. For example, one user update a particular data of node 1. Another user does the exact same thing at the exact same time, but for node 3. But when this peer-to-peer system synchronize and try to update, two nodes have been updated at the same time. Unfortunately, the timestamp is also same. So in this kind of cases, there are another alternative methods of handling these cases without using timestamps. But in case of using timestamps, there can be conflicts. So this peer-to-peer replication can have write conflicts, but the master slave replication totally eliminates the chance of update. Update means writing conflicts. But the disadvantage of master slave replication means the master. So if multiple users try to do update operations, master may reject all of those write operations, assuming that the system is busy. Everyone is trying to write, so I will reject everyone. Likewise, there can be a single point of failure in master slave mode. But in peer-to-peer replication, that kind of failure is less probable. We cannot say not, but there can be failures, but it is less probable than the master slave replication mode. So there is less chance for single point of failure of update operations, because the peers are there. There is no one to control. But there is this disadvantage of having conflicts. But there are other mechanisms of avoiding conflicts in peer-to-peer replication also. We will discuss those things later. Okay, we'll come to this title, consistency. So I have already explained this term in the very first lesson also. And a moment ago also I explained. So consistency is simply the agreement between the stored data of a given database at a particular instant and the retrieved data. Retrieved data and the data stored in the database. So in relational databases, consistency is very high because data is not replicated unless you have backups. In relational databases, the data is not distributed across different servers, but there is secondary storage backup in case the primary storage is lost or destroyed. I'm not talking about those backups, but when data is updated, and immediately if you retrieve data, then in NoSQL databases, this consistency can be less when data is replicated. Why? Because when you update a particular node, that update should be propagated to other nodes with the same copy of data is available. So if you assume that a given aggregate, so in NoSQL databases we can have aggregates. So assume that one person update an aggregate, and if this system uses replication, assume that the replication factor is 3. So replication factor is the number of nodes which the same data is replicated. That means if the replication factor is 3, same data is repeated in 3 nodes. If the replication factor is 3, same data is repeated in 3 nodes. So if you update one node, you must, the user will not update. That update should be propagated to the other 2 nodes also. So at the moment which the first update is done, it is not possible to update the other 2 replicas because this data is not there at the same place. One server may be at Sri Lanka, another server may be in America. So there is distance So the communication will take time. So these servers are connected by communication links, maybe fiber optic, maybe wireless, maybe satellite, anyway. So in communication, we have this parameter known as latency. Latency is what? The end-to-end delay in communication. So there is a delay in communication. That means when one node is updated, for the other nodes to be updated, there is a latency. That means there is a communication delay. Due to this communication delay, the data can be inconsistent. Why? If you update the node in Sri Lanka, then there is a latency until the node in America is updated. So until that node in America is updated, the data retrieved from the server in America is inconsistent, because that data is not the latest version of the data. The latest version of the data is in Sri Lanka. So if some user obtains obtain the exact same copied data from the node in America before the update is propagated to the node or the server in America, then that read operation done from the server in America is inconsistent. Inconsistent means does not agree with the latest updated form of the data, right? So that is the meaning. Okay, we'll see about this consistency. So write conflicts occur when two times try to write the same data at the same time. So I already told about this. And in addition to that, read-write conflict is what that I explained. So write-write conflicts are avoided by using different mechanisms. So I already told one way, that is by having the master slave replication mode or peer-to-peer replication mode. So in master slave, totally the write conflicts are avoided by using the authority of the master server. In peer-to-peer, there can be write conflicts if the same data is updated at the same time, but using different version stamps, these can also be avoided. So the problem comes in read-write conflicts. So read-write conflict is the one that I explained a moment ago, which can, when one client reads inconsistent data, that means for the example that I took, the client or the customer from America will read inconsistent data because another user has already updated the same data in Sri Lanka server, right? Okay, so the traditional ways of preventing this kind of read-write conflicts in relational databases is by locking data records. Locking data records. So the modern way or the better way of doing this is to catch these conflicts and fix them. So what is done in NoSQL databases is, so as I told you, in peer-to-peer replication, there could be this read-write conflicts because of the peer-to-peer replication architecture. That means when one node is written, if that update is not propagated to the other node, then there is this conflict. So there are approaches to detect. So the approach used in NoSQL is using version stamps. So we'll discuss about version stamps in a little moment. So this is the definition of consistency, which I already explained. That is the agreement between what is read and what has been updated. So that was the definition for relational databases. But for NoSQL databases, one additional factor should be considered, that is the replicas of data. So consistency is not applicable only to a subset of data in the server, but consistency should be there between replicas of data. That means if one replica is updated, then the other replicas of the same data should also be updated. Otherwise, the reads done from the nodes which have not updated will be inconsistent. That is the idea, right? In distributed systems, so this read write completes are there, right? So there is this concept known as eventual consistency. That means the system will reach the consistency eventually. So eventually means with time. That means in relational databases. In one of our previous sessions we did the lesson on transaction. So how to begin a transaction? You start the transaction, then you end the transaction with the keyword commit. So when you start the transaction, the data you have not committed, so it will not be visible for other users. Once you commit, it will be visible. But the fact is, just the moment, I mean, just after the moment you commit, that data will be consistent. So that is the nature of relational databases. The consistency is very high because there are no replicas. Just at the moment you commit a transaction, that data will be consistent. But it is not the case for NoSQL databases. It is more true if you have sharding, but we are not discussing about sharding. We are discussing about this replication. Replication is done usually in NoSQL databases. So there are many examples where replication is done. So this eventual consistency means just like relational databases, these NoSQL databases will not be consistent just after a transaction, but it will come to consistency after some time. So after the network latency between these nodes, after this latency, that means suppose that it takes 5 seconds for the update to propagate from node in Sri Lanka to America. So this 5-second latency will be applied. That means not just after the instant you did the transaction, but after 5 seconds, all of the replicas will be updated. So that means these NoSQL databases will take time to be consistent. Until that time, it will not be consistent. So there is a period which the system is not consistent. So that is what meant by eventual consistency. That means at some point in time, the system will become consistent. That is the instance where all the writes have propagated to all replicas of the node. So you can understand that when the replication factor is high, the time taken for the eventual consistency will also be high. When the replication factor is low, the eventual consistency will be reached within a lesser time. Right? So that is the meaning of eventual consistency. Right? Okay. So a client can read and write and then read a new value. Right? So that's what I already explained before also. This is difficult if the read and write happen on different nodes. So in NoSQL databases, the client does not know from which node it is reading. So assume that in this moment, client, if I am the client, I am writing. For example, I am updating some data in a column family store. I'm updating some data in a column family store which has a replication factor of 3. In that case, I may be updating that particular data in Sri Lankan server. But just after 1 second, if I try to read the same data, I may not be reading from the Sri Lankan server. I may be directed to the server in America. Because I'm in NoSQL databases, we don't know from to where we are writing the data, where we are reading. So at this moment, I may be writing to Sri Lankan server, and just after that, if I do a read operation on the same data, but I may receive the data from a different server, for example, the server from America. So even if the same user is doing a read, a write operation and then immediately read the new value, I may read a different value because of this fact, eventual consistency. Because we don't know from which server the data is coming. And if this eventual consistency has not read, we may retrieve inconsistent data. So that is a fact that you should know about NoSQL databases. So this is the theorem that I was talking about before. In short, this is known as CAP theorem, standing for consistency, availability, and partition tolerance. So consistency we discussed a moment ago. So what is availability and what is partition tolerance, you have to understand in this list, right? So, okay. So for the data to be consistent, right? So consistency, you need to involve many nodes in data operations, but this increases latency. So I explained that if you have multiple nodes, there is a high chance for increasing latency. Latency is the end-to-end communication delay. So there is a trade-off between the consistency and latency, right? So when the latency is low, take the case of, we'll take the extreme case of relational databases. So in relational databases, the consistency is very high, as I explained. Consistency is high, latency is low, because the data is not replicated. Data is only residing in one centralized server. When you update, immediately you can retrieve. But in a NoSQL database, which has multiple replicas, the consistency is low because of the eventual consistency, when consistency is low and the latency is high. Consistency is low, latency is high. So there is a trade-off between latency and consistency. So this is indirectly proportional to each other. That's what I wanted to tell you from this point. When you have higher consistency, you have low latency, like in relational database. You can imagine about relational databases. When you have low consistency, that is in the case of having uh, multiple replicas, the latency is high. When consistency is low, latency is high. You can imagine. So that is not the cap theorem. So this is an additional point. So latency is this end-to-end communication delay, which I already explained. This thing also I explained, as the relational databases have single server architecture. It has strong consistency and less latency. So consistency is an advantage, latency is a disadvantage. So having high latency is not desirable. Okay, so now we'll come to this theorem. CAP stands for consistency, availability, and partition tolerance. Consistency, you know. So what is availability? So that is the availability of the servers, or in other terms, these nodes which stores data for read and write operations at a given time. That is the availability. So assume that for a replication factor of 3, there are 3 nodes. If one node is down means the user is not able to have a communication with the server 3. Maybe due to different reasons. Most probably due to a communication failure or a server hardware failure. We don't know. So if one server is down, then we say that server is not available. Not available means the user is not able to read and write from that server. So that is the meaning of availability. So you can see clearly a trade-off between consistency and availability. If you have one node, if you have only one node, if that one node is down, I mean not available, then it will not be able to do any read or write operation. That means no availability. Availability is 0 if one node is down. For a case of factor of 3 replica, that means 3 nodes have same data. Even if one node is totally out, not available, there are still 2 nodes which can provide data to the user. But the disadvantage is consistency, as I explained in the previous slide. When you have multiple replicas, you have to go for the eventual consistency, and the latency will be high. So consistency will be low and availability will be high. Likewise, you can have, so that is an indirect relationship between consistency and availability. And what is partition tolerance? So this in NoSQL, all the servers are there as a cluster. Cluster is a group of servers. So cluster of servers is there. Partitioning means breaking this cluster into different partitions. So this cluster may be broken into different partitions due to communication failures. For example, if you have a cluster if you have a cluster and you divide the cluster into 4 equal parts and assume that one part is not able to communicate with other part, right? So there are 4 different parts of a same cluster and you break that cluster into 4 parts. Even if you break the cluster into 4 parts, then you may have one of these 2 parameters. Either you will have availability or you will have consistency. If you have, this CAP theorem states that out of these 3 parameters, only 2 can be achieved at a given time. So it says that if you have partition tolerance. So what partition tolerance is, you are able to achieve one of these 2 parameters even if the cluster is broken down into smaller clusters of servers due to communication failures or maybe other reasons. If the big cluster is broken into smaller clusters, even if still, if you have some availability, if the users within that small cluster can access data, access that required data, then that means it has availability. So this is true if the replication of data has been done. That means if the same data is, suppose that for this example that I'm talking about, the replication factor is 4. If the same data is copied into 4 servers residing in those 4 smaller clusters. So I'm talking about a case like this. So assume that this is the big cluster that I'm talking about. So I partition the big cluster into 4 parts. So there are nodes in different kinds of nodes in each cluster, like this. The number of nodes is not known, but so each of these dot is a server which can store data. So I assume the replication factor equal 4. So then that means if I say one particular data is in this server, the other data of the same copy of the same data is in this server. The copy of this data, I mean the replica is in this server, the other replica is in this server. Then there is no problem of partitioning this server into 4. So that means even, so there, assume that there is a user, say that user 1 want to access the particular data. Since this server is within this cluster, this user is able to access the data without any problem. But if it had not used replication, if the data, suppose that data is only in this server, then this user will not be able to access what is in this server due to this communication barrier. Due to this communication barrier, this user will not be able to access the data which he wants. But if you have used replication, then one of the servers in this cluster which this user has access contains the data, so the user will be able to access this data. So if you have partition tolerance, that means the availability is high. So these 2 factors go along almost with each other. right? If you have part, so these two factors are almost directly proportional to each other. So what can happen is, so if you have availability and partition tolerance, you will have to sacrifice the consistency. Why? So this thing I explained already. If you have replication like this, if you update a particular data in here, so if you update here, so it should propagate here. So it will take some time, T1. It should propagate to here, T2. And it should propagate to here. Maybe from here or here or here. It can come, but I'll take this case here. It should propagate here. So likewise, so the data in here will not be consistent until these updates are propagated to these nodes. So there will be time until these read operations will be inconsistent. So when you have partition tolerance and availability, you will have to sacrifice consistency. You will have to sacrifice consistency. When you have high consistency, that means not like this, when the replication factor is low, when you have high consistency, you will have less availability and partition tolerance. You will have less availability and partition tolerance. So that is what is specified this CAP theorem. So when you have high consistency means you can do a write operation and immediately, read after that. That means you have less replication. When you have less replication, the partition tolerance is low. When you have less replication, the partition tolerance is low. And the availability is also low, because if you get this kind of communication failures, when you have less replication factor, then the availability will be low. When you have this kind of communication barriers. So the CAP theorem states that the maximum you can have two features out of these three, right? So that is the idea of this CAP theorem. So this is the definition for partition tolerance. So I explained. So I'll just have given here the formal definition. So as I told you, it can survive the communication breakages in the cluster that separate the cluster into multiple smaller clusters, which is not able to communicate with each other, but there is communication with inside the small cluster. Communication within the smaller clusters is possible, but between these partition clusters is not possible, right? So this is the CAP theorem. So it states that given these three and partition tolerance for NoSQL databases, it can achieve two of them. So this is at most. You may have achieve only one also. You may achieve one or two at a time, but you cannot achieve, definitely you cannot achieve three. You cannot achieve all of these three at once. That is the summary of CAP theorem actually. You cannot achieve these three at once. You have to sacrifice at least one of them for the other. or maybe 2 sometimes, like in this case. If you want consistency, you have to sacrifice these 2. Likewise, it will come. So this I have also given you an example also. So if it is partition tolerant, high replication, you have higher availability but less consistency. That the case that I explained a moment ago, right? So no need, I will no need to explain it again. So I explained that part. Okay. So having known about the distribution model of NoSQL database. So what is the distribution model? The summary. So the data can be sharded or replicated. Sharded means same collection of data is broken down and stored at different places. So in that case, if the same is broken down and stored at different places, so what will be the, so for sharding, how is these 3 parameters are going to affect? So the consistency is high, and the availability and partition tolerance is low. Availability and partition tolerance is low. So that is how it is going to affect for the sharding. Because sharding distributes the data. That means breaks the data and distribute among different servers. So due to that, the same is not replicated, but it will distribute. So when it is taken in common, the breaking of one or the non-availability of one will not break the whole system. Will not break the whole system. That means if you want to obtain some data from a table, some of the data in the table may not be accessible because of non-availability of some nodes, but most of the data will be available because availability of other nodes. So in that case, the comparison of this consistency, availability, and partition tolerance is a bit different than we discussed for the replication. So we discussed this case, this special case for the replication. So in replication, when the replication factor is high, the availability is high and the consistency is low. In sharding, when it is taken overall, so the same, the data is broken down and distributed in everywhere. So it is having a kind of partition tolerance, and some may be available, and the consistency is a bit low because data is distributed. So for the data to propagate, it can take time. So in sharding, the analysis is difficult than replication, as the breaking down of data and distributing. So it is not simple like replication. So we need not to discuss about sharding. So I took the example for replication, right? So sharding is complex. So these 3 discussion of these parameters is also difficult because of distribution. So partition tolerance may be high or low, depends on data distribution, how that data is distributed, whether that data is distributed across the whole cluster or whether that data is distributed across a minor amount of nodes within the cluster. So that depends on the distribution way that the sharding is occurred. That is complex, right? So we'll take these 4 kinds of databases. I mean, first we'll take the aggregation data model for NoSQL and discuss each key value, column family, and document type databases. And we'll, for all cases, we'll have a comparison between the relational model and the specific NoSQL model. How is those terms differ? And also we'll discuss some examples and this structure. I mean, there is no definite structure, but there is this way of having this key value stores, right? So when you compare the 2 cases, relational and the key value databases, so in what is called the instance is called as a cluster. So this is not the cluster of servers, but this is just a term for an instance in relational database. So a table is known as a bucket in key value databases, specifically in this database management system known as RAC. But this is not the only database management system for NoSQL. There are others: RAC, Redis, Mermshed DB, Project Voldemort, Aerospike. Likewise, there are a lot of examples for the key value databases. So for this case, it is known as table is known as bucket, and row is nothing but a key value pair. So what is contained in a row is a key value pair. As the value, you have the aggregate. So what you have as the table is shown. I have shown using this red color line. And within this bucket, you have different rows. In this key value stores, it is a key value pair. It is this blue line. So there are multiple key value pairs. And within this key value pair, you have a key which contains these values, key value pairs. So this is a key value pair. And so it is identified by the key. Key is the one which identifies a particular row. Key is the one which identifies a particular row, right? So values are there in the rows as aggregates. There can be 1 value or 2 value, or there can be some aggregates inside these values also. So a value, 1 value can be an aggregate also. That is how these hierarchical databases are designed. They can have aggregates within aggregates. So this is a key value pair, and within that key, it encloses. So the key will point to a set of values, which may also contain other key value pairs, or maybe it is a simple value. We don't know. Okay, so what is how this is going to identify a row is using the identifier used for key. So this key value store is like an index in a relational database management system searches for a particular record. This key value, so key will act as something like an index which points to the row which contains the value, right? So That's why I have given here, it is like a primary index mapped to ordered data file in relational databases. So in primary index, if you can remember, in primary index, there are block anchors pointing to blocks which store that particular key. Just like that run, in this relation, key value stores, the key points to the particular row. In the primary index, it does not point to each and every record, but it points to a block. Then you have to find that particular record in the block. So it is not totally similar, but there is a kind of similarity. So here there is for each and every record there is a key, right? So you don't have to look through the whole, I mean inside the aggregate. So when you have the key, you can find the aggregate. But the fact is, for key value stores, you cannot retrieve part of the aggregate. There are some another aggregation models like column family stores and document type databases. Some of those database management systems allow to retrieve part of the aggregates also. So that depends on the database management, NoSQL database management system used, whether retrieving part of the aggregate is possible or not. Because in the general definition, the aggregate is the unit which is the upper limit for a transaction. So in relational model, a given table, it can consist of multiple rows, is a limit for a transaction. That or maybe you can join tables and do transaction, right? So you can join tables and form another table and do a transaction on that table. Likewise, the transaction involve multiple rows in relational database, but in the definition of NoSQL, there is no definition, no specific definition actually. But in the general definition, I explained last week that aggregate is the limit for a transaction in NoSQL databases. But that statement changes depend on the database management system. Some database management systems also allow some part of the aggregate to be retrieved. So, but still that the limit is aggregate. That did not change. But many database management systems bring the whole aggregate at once, then analyze that aggregate, update, or do whatever the operation. But some database management system, it will allow the part of an aggregate to be retrieved. But in key value, it is not true. Key value doesn't allow, but we will discuss in a moment some database management systems for document and column family stores allow that to occur. Okay, so whether to use key value document or whatever the database management system or the NoSQL database depends on the use case. So these are most suitable for these use cases, which is to store session information, user profiles, and shopping cart data. So you may have come across these in different times, but you may have not known what kind of database was used to store your data. So if you have done online shopping using eBay or any other platform, Daras or whatever, so you have a shopping cart. So that shopping cart information can be stored using this key value store. How? So the shop item one, so it can have a key. So this is the key. Using that key, the item one's information can be stored as a value. So the item one can have a name, it can have a production year, it can have a manufacturer, and the item two that you buy can be totally different to item one. It can be another one. This may be an electronic item. This may be a textile item. So the properties of these two items may be totally different. But it does not matter in key value databases. So it will allow. But you cannot use relational databases. So if so, you have to create columns to match the highest possible number of attributes, and when you don't have data, you have to keep null. That is a wastage, right? So just like that one, the other use cases will also allow user profiles to store user profiles, and for storing login, usually login session information. Right, so as I told you, this software vendor to vendor, some limitations on this vary. Software vendor means what kind of database management system you are using. Right, some features will vary in a little, not much, but some little minor features may be vary. Okay, so what is not suitable is, for operations done within the aggregate is not suitable for this key value, and also for other aggregation types of database. That means if you want to query by using what, for example, in this shopping cart, if you want to query on the item property, such as the number of items bought, or maybe the manufacturing date of item. Likewise, it is not disabled. So what is suitable is to bring this whole aggregate at once. Bring this whole aggregate at once. But if you have some operation between the aggregates, that means this item and this item. If you want to query between this item and this item, if you want to have relationships, that is not good. These key value stores are not good for that part. So I have already explained this point. This value is nothing but it can store any kind of data without a schema. In relational, you have a schema. Here, you don't have a schema. You can store anything. So, if so, this is also a fact which depends on the particular database management system. So in relational databases, you define domain for these values. So in NoSQL databases, we don't usually define the domain. The domain is undefined such that you can store anything. You can store anything. But sometimes you may be given the permission to specify the domain for some attributes. So in such case, if that database management system allows, so in that case, this become a domain bucket. So this is a bucket, no, the table. So if this the domain of this value can be specified, then this bucket is known as a domain bucket. But this fact, whether it allows a domain bucket or not, depends on the database management system. So for different key value database management system, the implementation will vary. So based on the database management system that you have been given, you have to think what is allowed and what is not allowed. So we come into the second type of aggregation model databases, or in other terms known as hierarchical databases, that is document type databases. So first we'll have an analogy between the model that we know. Instance is already known with the same name. Table now is known as collection. Row is the one which is known as document. Row ID is simply the ID. So the things that you should remember is table is known as a collection here, and the row is known as a document. So in key value pairs, it was just a key value pair. Here you have a special name for a row known as document. So these are usually typically used to store this hierarchical data structures such as XML, extensive markup languages, which is used for markup languages. So you may have learned markup languages in your previous module, such as HTML. So in HTML, within one HTML opening tag and a closing tag, you have other embedded tags which open and close. For example, P, paragraph, open and close. So likewise, you have aggregates within the document. So the HTML code that you write, or this XML code which you, so I'm taking HTML because you have the experience to HTML. So for HTML, that HTML document can be stored as a row. That HTML document can be stored as a row in this document type database, where your HTML document will have embedded aggregated document, where you have a hierarchical data. That means you have blocks. Within the HTML blocks, you have multiple blocks. Within those blocks, you have other blocks. Likewise, you have hierarchical data structure. So for storing such kind of data, this document type databases have been designed, right? So the examples are these: MongoDB, AlongoDB, CouchDB, PostgreSQL. So some of these database management systems I have given you for your mini project. So some of you may have already experience with these database management systems by this moment. So what does this do is, so just like the key value databases, it looks for the aggregate. So the aggregate is the document. Aggregate is the document. So it looks for the aggregate based on the ID. Based on the ID. And as I told you before, in these document type databases, partial retrieval or retrieving part of the document is possible. For example, if you want to get some part of HTML document without bringing the whole HTML document, you can bring some block within the HTML document using this document type database. Okay, so but the schema is still undefined and it can differ. It can differ. That means one row of this collection is the table name for document type databases. Within the collection, you can have heterogeneous documents. That means one row can contain an XML document, another row can contain an HTML document, another row can contain another type of document. So likewise, different kind of document can be stored. So there is no definition for what is contained in this document. So what is, so the more, to ensure maximum, I have already explained this in previous. So to ensure availability, it uses replicas in master slave mode, right? So in sharding, it is pretty sure that as the data is distributed, when one node of the whole big cluster is not available, if the data that we are searching for is stored in that particular node, then the data is not available to be read and written because of failure of that node. So there is a probability of failure in sharding, but in master-slave replication, it ensures availability. So this document type databases uses master-slave replication mode. So it is usual, the usual practice is using replication than sharding in these kind of databases, right, for document databases. So the same thing, same general rule applies. So it is repeated in each and every time. So the transactions are only allowed at document level. So what is a document? Document is an aggregation. Again, the same thing is repeated. It is allowed only at document level, which is in aggregation level. And these features, commit and rollback, are unavailable. Why they are unavailable? There is, as you have replication, there is no meaning in having commit, because even if you commit, until that eventual consistency occurs, data is inconsistent. Even if you commit, there is no guarantee that data is consistent because of replication and latency, right? So these things I explained already. So this also has some use cases. So in addition to the previous case that I told you, so event logging, that is to store events. So for example, say for a website, so you one can track what are the events that occurs in a particular website when one user visits that web page. Okay, that event was recorded. So the user ID is this one, and this as the document, it will store the actions performed by the user. Logged in, then open this link, then perform these actions. Likewise, it can store it in a document. So likewise, so these are the other applications, e-commerce applications and real-time analytics. So this real-time analytics is a feature. This is used, the best example is in YouTube. Real-time analytics is used to track the viewers, subscribers in YouTube. So these document type databases are used in those applications, right? So using a document type databases for these applications is very easy due to the non-available, not being having to define a schema, to not being having to define a definite structure. You can store anything as the aggregate. That is the freedom of these NoSQL databases have allowed these applications to use these databases, not relational databases. So for these use cases, relational databases can be used by defining the schema, but that will involve a lot of effort to define a particular schema which can cater to all the requirements of the use case and provide those constraints whether it is allowed to keep null, etc. But some use cases may not be able to be entered in the relational schema. Likewise, there will be problems and difficult. Due to the difficulty, relational database management systems are not desirable for these use cases, right? And the same thing, repeating, not suitable for transaction between the documents, simply between the aggregates. So this is the same category, the aggregation data model. But the difference is you have columns, right? In the previous cases, so we'll first have a look at what is this analogy between relational databases and this. So instance is known as cluster in column family stores. Table is known as simply a column family. Table is known as a column family. And the row is same name, row, and column is same name, column. Database is known as keys. And so this is somewhat similar to relational databases, but not exactly relational databases, because so a given row is identified by a key. So this can be compared with a primary key of a relational database. Okay. These two features may be similar. The row is identified by a key. In the RDBMS also, relation database management systems also, it is identified by a key. But the fact is, the number of columns for each row can be different. For example, this row X can have 2 columns. This row Y can have different number of columns, and the values, as the domain is not specified, this column 1 can have 1 value, and this column 1 in this row can have another value. This can have 1. This can have another value. I mean, another domain. There is freedom. And also, in relational databases, this element for a given row and given column, this is an element. An aggregate was not possible within an element. That means when you consider one value, so there is a column name and there is one value. So here also there can be another aggregate. That means so those columns are known as super columns. So within a column, it can have multiple columns. That means as the value, so as the value of a given column, it can have another name value pairs. So name value pairs can be embedded within a given column. So those are known as super columns. So those are the differences. So even though the rows are columns, they are just like relational databases, domain is not specified and the values are not atomic and single value. Multi-valued, there can be multi-valued, non-atomic aggregates. And the number of columns are not fixed. You can have any number of columns you want. So those are the differences. And these are the examples of database management systems. Apache Cassandra, Apache Space, Hypertable, Bigtable. So those are some examples. And the fact is, so row-wise writing is efficient. Why row-wise writing is efficient? Because the row can be identified easily just by one operation using the key. It is so writing to a column, that means using a row, because the row is identified by a key, you can identify the row and then just come to the column is easy, but the column wise reading just like that one, the column wise reading is efficient, right? So you can read by column. You can, but the reading column row wise is less efficient, and writing column wise is less efficient. That is because these columns have aggregates. These columns can have aggregates. So this row is having an aggregate. So these three are aggregate, because the rows aggregates are read at once. Aggregates are read at once. And in this, when it is writing in row, so you can access a row using a key, then you can write to each row. Sorry, each column. You can write to each column, right? So what it does is it will store group of columns to all rows as the basic storage unit. So this is the group of columns for each row, and the number of columns can be different. Okay. So it is a two-level aggregate structure. Why two-level? The first level is this row. I mean, what is shown in this yellow colored boundary. So this is the first level, where you have the row key, and this is the value. This all columns are the values. All columns are the value. Second level is the what is inside columns. So what is inside column? Name value, name value, name value. So this is the second level aggregation. This is the second level aggregation. What is contained in a column within a row is the second level aggregation. The first level aggregation is the row itself. Key and value is all of this. Value is all of this. And the second level aggregation is what is inside this column, name value pairs. So that's what I have given here. First key is the row identifier. Second level are the row, the columns. Column has name value pair. Column is identified using a name. So those are the second level aggregates, right? So this is what I have told you earlier. It can have different number of rows, not fixed, like RDBMS. This is same. I'm repeating the same thing. Transactions are atomic at row level means this aggregate level, right? So this is what I had told you before. Within this second level aggregate, which is this name value pair, this value can contain another aggregation of name value pairs. That means what I am pointing here, value 1 can contain another pairs of name value pairs. So in that case, this column is known as a supercolumn, which is an aggregate within an aggregate, right? So for those columns which have, for those rows which have less number of columns, those are skinny columns. Others are known as wide columns. That means because in column family stores, the number of columns can vary. When the number of columns is less, it is known skinny. Otherwise, it is wide. And what is mostly used distribution model for column family stores is peer-to-peer replication. So these are decided based on the application, right? So this default distribution model is selected based on the application. So you can see many NoSQL database management systems use replication rather than sharding, because sharding has disadvantages. It is not usually partial tolerant. Replication is used for handle partial tolerance and to achieve high availability. But you have in having replication, one thing is sacrificed according to CAP theorem, that is consistency. Consistency have to be sacrificed. Right. So some of the applications already, the applications which can be used for document type databases can also be used for column family stores, because these belong to the same category of the aggregation type NoSQL databases. So the use cases can be similar. So these use cases appeared in the previous discussions also. So for the event logging and block entries, previous database models was also used them. And for column family, as it is an aggregation data model, so those use cases, same use cases can be used for these column family stores also. Okay. So that is the end of discussion about aggregation type databases. Right. So now we have come to graph, or in other terms known as network model databases. So what was known as a relationship is also called a relationship in graph databases, but it becomes something known as directional edge. So directional edge is something like this: an arrow in graph database. So how relationships were implemented in NoSQL databases? In entity relationship model mapping to the first normal form or relational data model, I told you that relationships also map into tables. So you have to map the relationship in ER diagram to a table with some schema-based constraint. So the schema-based constraint which is used to establish the relationship is usually the foreign key. So you will have to use not only one table, you will have to involve two tables with the foreign key, two tables with the foreign key, or maybe if the relationship is a tertiary relationship, you may have to include three tables. So I took two tables, that is the usual case. So two tables with a foreign key, that is how you implement relationships in relational databases. So in graph databases, the graph database is totally concentrating on relationships than the content. So in aggregational databases of NoSQL, within maybe a bucket, maybe a column family store, within some entity, there were multiple rows. But in graph databases, usually for a given unit, there is only one row. That means within a given unit, there is less data. What is more emphasized is the relationships. What is more emphasized is the relationship, not the data, right? So in graph databases, what this unit is usually known as the node, right? So this row in relational databases maps to a node, and node is the unit. So within between different nodes, you have different relationships. So more than what is contained in a node, it is the relationships which is more emphasized in a graph database. That means where the use case is when you have complex relationships, that means thousands of relationships like a graph. For example, like in a social network, right, where one person can have multiple friends or other peers, right? And these relationships may have their own attributes, and these nodes can also have different properties. So the nodes can have properties. These relationships also can have properties. This kind of complex graph is difficult to be implemented in relational model, because relational model usually involves with it can barely handle 2-3 relationships by joining tables. If the number of relationships goes beyond that, relational model will fail, because the relational model or even the aggregation model will fail. Aggregation model even cannot handle relationship between rows of the same table. So how can it handle relationship between different tables? The aggregation model cannot handle relationships at all. The relational model can handle relationships to some extent. But as a single unit or a table has many data or rows, when you have relationships, even 2-3 relationships, the process becomes complex. But as the graph databases has only one row of data called node, this graph can successfully handle relationships with less complexity than any other data based model. So that's why these graph databases are used when we have complex use cases. So these are some examples for database management systems for graph databases. So GraphDB, Neo4j, Sparksy, Redis Graph, or DNDB. So Neo4j we will discuss in next week as a documentary, right? So I may test you in using Neo4j. And for the aggregation model, I will demonstrate using Cassandra, Apache Cassandra. Right, so I advise you to, even if you don't have it for the assignment or the mini project, I advise you to install them in your machines, as I demonstrate to you using those two database management systems, Apache Cassandra and Neo4j. So next week, please install and keep it, right? Okay, so we continue this discussion on graph databases. So these also support ACID transactions, and the transactions are not, in this case, limited to rows. The transaction can go up to the whole data, I mean, whole graph. If you want, you can retrieve the whole graph at once. You can retrieve the whole graph at once with relationships. The acidity of the transaction, I mean, acidity means is atomic, consistent, isolated, durable. Features of the transaction is not limited to a row, like in aggregation model. It is not limited to a row. It is it can extend up to the whole graph, right? So that is the meaning of that point. So first, now we'll have some analogy between aggregation and this model. So in aggregation, it can, if you take a row of an aggregation model, that means a single row can contain large amount of data. So when you compare it even with the relational model row, so if you arrange the size of row of relational model, aggregation model, and graph model has the least size. Relational model row size is the average size. Aggregation model row size is the largest size. If you take the number of relationships, graph model has the highest number of relationships. Relational database model has the average or the medium number of relationships, and the aggregational model has the least number of relationships. So you can see that relational model resides in between the two extremes. So the two extremes are the aggregation model and the graph model. Two extremes are the aggregation model and graph model. Relational model is some combination of aggregational, I mean, these two extreme, aggregation model and graph model. So relational model can be considered as a universal model which can be applied to any use case by adjusting. But this graph and aggregation model are application specific. Application specific. They can be applied to only for given use cases, as they have extreme features. Like for graph databases, it has very small records but many connections, right? So this is what I have given, small records with complex interactions. That is the feature. But in aggregate, large records with almost no connection even between the adjacent rows. Even between the rows of the same bucket, it has almost no relationship, right? So those are the extremes. So it is simply a graph database. It is simply a data structure consisting of nodes connected by edges. This means relationships, right? So as I have told you, it is suitable for complex relationship use cases. And I told you relationships can have properties. So compared to relationships in relational databases, it takes less time in graph databases to navigate and retrieve using queries. But the insertion time is high. So this point was even true for relational databases, wasn't it? So you saw that when we have operations involving multiple tables, when we have operations involved in multiple tables, so the data insertion time was high. So that was the even you could observe when we were doing normalization. So normalization increases the number of tables. number of tables. So the insertion time will be high. So that just like that one, in graph databases, querying is easy because of the relationship. You can navigate to each and every node using the relationship. So it takes less time to retrieve and navigate using queries, but data insertion time is uh, relatively high because first the node should be obtained, and inside the node there are properties, then those properties are required to be changed. So there is time for querying and then insert. So the insertion time is relatively high. Okay, so this graph databases usually uses the master-slave architecture for reading and writing. So it uses master-slave architecture. So what is master-slave architecture? So it is an architecture which is used in replication. So that means the information in a graph is repeated in other servers, and it uses a master to appoint a master and to control the writing operations basically, rather than reading. Reading is master is also involved in reading, but not much given priority to reading, but to handle write conflicts, master is involved. So for these graph databases, the replication mode involved is master slaving, the default one. So you can see for almost all the database types of the NoSQL with the graph or aggregate models, it use replication rather than sharding because it has the feature of availability in by using replication. And sharding is even more difficult than it is for aggregation databases in this graph database. Why? The reason is graph database, the relationships within a single node is even difficult. So if we want to, in sharding, the data is broken down and distributed. If you break down data within a graph, then you have to store them as different graphs, and then you have to remember the relationships also within different servers of the same cluster. So when you bring back, then you have to bring back and then create the relationships. So that will take time. So sharding is very difficult in graph type databases. So replication is the one it is used in graph databases. Even in aggregation data models, in most of the architectures you saw that replication is the one used rather than shard. Right. So this adding or removing a node, not only one node, maybe one or two or a set of nodes, or maybe removing a relationship, or maybe removing an attribute, all of this occur as a transaction. So the limit for the transaction is the graph. It is not limited, as I have given here, it is not limited like row or node in graph database. This is not limited to a single node. A transaction can involve multiple nodes, multiple relationships, and it can involve properties in the relationship, or it can involve properties of a node. It can involve in. The limit is only the graph, right? So these are the use cases. So for social networks like Facebook, and this example you may be very familiar. For Google Maps, when you are moving in a vehicle, you often use Google Maps to find the path to a given location. So you, as a vehicle, is a node. You are a node in Google Map, right? So your location, so you have some name, you maybe have some name, and your location is the main parameter of your node. Your location is the main parameter, and the other node is your destination. So other node is your destination. So your node, which is having your moving location, and the end location is the other node. So the relationship between these two is implemented using a graph database. So in Google Maps, what is implemented is a graph databases of many and many nodes. When you connect to Google Maps using your phone or whatever the device you have, what you are doing is you are creating a node in the existing graph. You are creating a node, and when you move, what is changed? What is changed is the relationship properties. What are the relationship properties for this specific application? That is the speed, the distance between the endpoint and you, and the time of arrival. So those things are the properties of the relationship. So when you arrive at the destination and when you exit the Google Maps application, your node will be deleted from the graph. Your node will be deleted from the graph. When you re-enter, your node will be created, and you may have seen in Google Maps, not only one application, one destination, you can have multiple checkpoints between your location and your end location. So these intermediate checkpoints are some another nodes. It is added to the graph, big graph maintained by Google. So you can imagine graph databases. The big example is, so this Facebook is also a good example. Rather than that one, I think Google Maps is a very good example to imagine about graph databases. And the recommendation engines also work like graph databases, right? When you when you type something in some recommendation engines like Google, so these work on by using this graph database. So these are some applications which these graph databases are used. Like, so as the time for today is up, so we will discuss about these versions, terms and transactions, and then we'll move on to map reduction in next week, and we'll start a demonstration using Neo4j and Cassandra. Then your syllabus will be over, right?